So this is the final section of solving linear simultaneous equations, and we're going to look at just two final examples. So as we know, there are two ways we could solve the above. We could either write the explicit solution. This is the case where it's overdetermined and it's inconsistent and the rank of A is full rank. So we can write this explicit solution, or we could use the pseudo inverse and find that from singular value decomposition. The question, we prefer to use B rather than A because of numerical errors if we invert this when A is close to rank deficient. But what if we don't have the computing power to do this inverse or to calculate the SVD? And this could happen where A is a very large matrix and we have some sort of, I don't know, say IoT device with very low computing power. So we could have a look at a simple iterative solution. So one solution to the above is use gradient descent. There's the objective function. There's the surface we're trying to find the minimum of. So at the kth iteration, we're sitting here at this point, and we're looking at that value for the objective function. So what we do at the next iteration, we're going to take the x of k and we're going to move it in the direction, the negative direction, minus the gradient times mu, which is the step size. And if we differentiate that dj by dx, we get an expression for the gradient. And then we plug that in there and we get this pseudocode here. So that's all it is. It's extremely simple. It's really just two lines, isn't it? Two lines of pseudocode to actually track down. Now, if you make the step size small enough, it'll just track slowly down the side and maybe roll up and roll back and up and back at the bottom. If you make it a little bit bigger, it'll go like this. And if you make it too big, it will go like that and unstable. So you've got to choose the right value of mu. So here's an example. If we take these values for A and B and we start at the origin, and we know the solution is going to be 0.5. Let's see when we get what we get when we do it iteratively. So I've chosen mu equals 0.01. And you can see what happens. You get some oscillations at the very beginning, and then it sort of settles down and goes down to the value 0, which is for x1. As you approach k, the iterations approach infinity. Similarly for x2, you get some oscillations at the beginning, and then it goes up to 0.5. So I've zoomed in on those oscillations from 0 to 100, and you can see them there for x1 and for x2. So if I didn't want those oscillations for whatever reason, how could I deal with that? Well, I could try changing the value of mu. I've put that in red because I've changed it. So I've gone from 0.01 to 0.001. So now it should track down nice smoothly down the side. And I've just looked at the first 100 iterations to check if there's any oscillations. There's no oscillations. Of course, the downside is I've managed to get rid of the oscillations, but the problem is that I haven't reached the true value yet. This is supposed to go up to 0.5 and this is supposed to go down to 0. In fact, as you can see, it takes roughly 10,000 iterations, whereas previously with 0.01 it only took about 1,000 iterations. So the trade-off is you get a smoother movement down the side of the bowl, but it takes longer before you reach the true value. What happens if I go to mu equals 0.012? So 0.01 was fine. After 1,000 iterations we found the true value, but if I increase it only slightly, 0.012, you can see what happens. Look, this is 10 to the 6. x1 and x2, they go unstable. So you've got to be careful how you choose mu. Now, the other thing that could happen is that we've assumed the A's and B's are constant. What happens if the A's and B's were changing? Then effectively the bowl would sort of move around, and you could track that by doing it iteratively. There's lots of issues that can occur here, so if anybody's looking at tracking a non-stationary process and they say, whoa, this is much too simple, this is just a tutorial about solving least squares equations, and I'm just showing where you can go with this problem. And this leads to more advanced topics like recursive least squares, the least mean square algorithm, which is a stochastic gradient algorithm, and in general adaptive filtering. So another issue that can happen is the effect of measurement errors with a x equals b. In particular, errors with the b vector. Now, we talked about this before, and we said how small errors in b could lead to large errors in the estimation of x if a was ill-conditioned. And what we mean by ill-conditioned is that if the ratio of the maximum singular value to the minimum singular value is very, very large. If it was a square matrix, we could look at singular values as well, but we could also look at eigenvalues, the eigenvalue spread. So let's assume that we have some mixing process where the output y is equal to a1 times w1 plus a2 times w2. w1 and w2 are the inputs and y is the outputs. And what we'd like to estimate is what are these a1s and a2s. So one way of doing that would be to keep putting in different inputs and keep measuring the output. So how do we do that? Well, let's assume, what could this practical situation be? So imagine it's some sort of physical chemical reaction we wish to measure, and let's assume the temperature of the solution is equal to, these are the concentrations of two different chemicals that you add, and they mix together according to some linear process like this, and we want to find out what A1 and A2 are. So if you had exact observation measurements, etc., etc., and there was no noise or errors or calibration or whatever, then W11, W1, W21 that's the concentration of the chemicals for the first go, that's for the second go, that's for the nth go. And if there was no errors whatsoever, you would only need to do it twice, wouldn't you? Because you'd have two equations and two unknowns and you'd get the answer. But that's never the case. There's always some errors, so we overdetermine. Now, let's have a look. This is what we can measure. We can measure the temperature, and we know what these are. So this is like training data in wireless communications, but I've taken a different type of example here. And let's assume we are estimating x by a pseudo-inverse times b. Now, what happens if we have some error with the observation? Let's assume that measuring the temperature, there is some error in the way we measure the temperature. How will that affect our estimate of x? Okay, so now we have the situation above, and we want to assume that there's going to be a delta b error in the vector b, the observation vector b, and how is that going to affect the true x? So we can write the change b plus delta b here, and this gives you x plus delta x, and it's simple to show that delta x, the change in x, will be the pseudo-inverse times delta b, the change in b. Okay, so let's have a look at the equation above. And what we've got here is a pseudo-inverse times delta b. Replace a pseudo-inverse by the expression you've seen many times before, and we get this, where a is the singular value decomposition is given by that. Now, if we had a very small sigma I, say sigma 4 was very small, then you might expect that would make that very large and give you a large delta x. But what we're doing is taking the inner product between mu of 4 and delta b. So if that inner product mu of 4 delta b is very small, then this whole thing isn't necessarily going to be very large. However, if you've got an inner product between mu of 4, u of 4 and delta b, which is larger, then this could make this very large. So we're interested in two things: whether any one of these singular values is small, and whether this inner product is going to be looking at towards 0, or whether it's going to be larger. So let's take a couple of examples here. Let's look at this case. So here this is the very small singular value for u of 2. What we're looking at here is when n is equal to 2. By the way, what is n? We've got an m times n matrix A, and so it's overdetermined, so n is the lower dimension. So we've assumed the rank is n, and that's full rank. So it goes from I equals 1 up to n, which is full rank. So in this case, we've got a 2 by 2 matrix. And we've got the singular value sigma 2 is very small. So what's the inner product u2 delta b? So u2 is like that and delta b is like that. So they're almost collinear, right? So that would be significant. So you wouldn't really want to use that. What about this one? Here we've got sigma 2 is 0.0001, but look what delta b is. So delta b and U2. So U2 transpose times delta B, that's almost 90 degrees. So that's going to be quite small. Why is it going to be small? Because U2 transpose times delta B is given as the modulus or the norm of U2 times the norm of delta B cos the angle between them. And cos of something that's nearly 90 is going to be 0. Nearly 0. Now what about this? Here we've got a very small singular value. And in this particular case, again, they're almost collinear, so we wouldn't want to use that one. So this one wouldn't be a problem, but these two at either side would be. So now let's put in some values for A and B, etc. And let's see what result we get. So if that's A, you can show what the singular values are 8.0622 and sigma 2 is 0.0001. So we've got a very small singular value. So we've got the potential to have a large change in X for a small change in B. So if we let B change to B plus delta B, and I've drawn in red the bit that's actually changed. So X, this top bit hasn't changed, but the bottom one has changed, not by a lot, maybe 10%. Okay. So what's X plus delta X going to be? Well, you put it through there, and you find that X plus delta X looks like this. So if you compare that with the original X, it's quite a huge change. And if you work out the delta B and the delta X, you find that this change in B gives you this change in delta X. So that's a situation where you get a large estimation error in X because of the ill conditioning of the matrix A. So the way around this problem is to use what's called reduced rank approximation for the pseudo-inverse. So if you look at the expression for X plus delta X and put in the expression for the pseudo-inverse, you get this. There are two terms because it's a rank 2 matrix. And the problem is coming from the fact that sigma 2 is small and U2 transpose times delta B is reasonably big. So we'd really like to get rid of that term. Now if you get rid of that term, it's like writing the pseudo-inverse with just one term instead of two terms. So you're effectively, it's called a reduced rank approximation. So there you are. I've changed that to 1 instead of 2. And if I go ahead and do that, I get this. So delta X turns out to be that. Now compare that with the case when I used the normal expression for pseudo-inverse. So the previous delta X was that when I was using the full rank implementation of pseudo-inverse. And here I've reduced delta X to that. So I could only do that if I knew which singular value was going to cause a problem, and that could be to do with the fact that I know something about the calibration or the errors that might occur in any of the equipment that I'm using, and I would have to do that in advance. Okay, we've come to the end of this short presentation, and before I start, I suppose I should mention this guy. He's called Gauss. And Gauss is the one who really laid the basis for least squares, certainly in the 18th century and early 19th century. So we should give a big round of applause to him. So we started off by just looking at how you fit a straight line to a set of data points, and we talked about underfitting and overfitting. And then we looked at AX equals B and said that could represent a set of equations, and we want to find the solution or the least squares solution. And in the end, we ended up saying that the least squares solution was equal to the pseudo-inverse times B, and this gives you the minimum norm solution, which takes into account every possible case. So we did some visualizations, and in particular we looked at the objective function as being a multidimensional quadratic. I've drawn it here as a function of two variables. Of course, it could be hundreds or more variables if it was a machine learning application. And I looked at different ways of solving this equation here, giving you an explicit solution. And you can do that by either using the orthogonality principle, the projection matrices, or the null space of A transpose. And each way just gives you a different insight into the problem. And that's why I think it's very useful to approach a problem, even though you can solve it equally in any of the three ways. It just gives you a different insight into what's going on. The next thing we did, we said, well, why don't we weight the error terms and give different weights to different error terms? And we also looked at regularization. And what that is, dealing with three main issues: the fact of lack of unique solution. The other main issue was that you have overfitting. And then the other issue was that you get ill conditioning of A, which can give you large errors in X if you have an error in B. And one particular type of, this is the L2 regularization. If you have L1, we call it lasso, and one of the problems with that, one of the issues that can give you, is that you can have a lot of sparsity in the solution vector, so a lot of zeros in that solution vector. I looked at the idea of constraints, using constraint optimization. I looked at linear constraints and quadratic constraints. And then I looked at how you could find an iterative solution if you didn't want to either use an explicit formula or take the pseudo-inverse. And finally, as I've just mentioned, the effect of small changes in B can give you very large changes in X, depending on whether a pseudo-inverse is ill-conditioned or not. And one way of getting around that is regularization. So that's the end. So thank you for listening. It was only a tutorial, but nevertheless, I hope that you learned something. And I hope I didn't make too many mistakes.